Welcome back, and we're going to continue on with another example. This one is like a classical example of all classical examples when we're talking about related rates. So we have a 17-foot ladder is leaning against a vertical wall. So, okay, I need to get my picture going. And so here's the ground, here's the ladder, and we're going to say that this is 17 feet. Okay, leaning against a vertical wall, so that's a 90. Okay, I can see I have a right triangle. This is good. The ladder starts to slide down the wall, so it's going down the wall. This top part is going down the wall at a rate of 2 feet per second. And we're wondering at what rate the base of the ladder is sliding, so we're looking for how fast it's going this way. Let's see, sliding away from the wall when the top of the ladder is 8 feet above the ground. So it's sliding down, but we're looking at the specific moment when this is 8 feet. Okay, and then that's all we're given. Okay, so we have some work to do. Okay, so I did my diagram. Step 3, I want to label everything that I have in this problem. So for our purposes, I'm going to call this X, I'm going to call this Y, and I'm going to call this Z. Okay, and I don't know what X is right now. I know that Y will eventually be 8, and I know that Z is the length of the ladder, which is 17. Okay, and now if I think, I know I'm going to have time derivatives in here somewhere. So what is dx dt, dy dt, and dz dt? Okay, dx dt would be how fast it's moving horizontally. That's actually what I want to know. Okay, dy dt is going to be how fast it is falling, and I'm going to say that that's negative because of direction 2. Okay, and then dz dt would be how fast or how much the hypotenuse is changing, and the ladder isn't getting any longer or shorter, so this is actually 0. Okay, now x, I actually can find that, right, by the Pythagorean theorem, which is our equation that relates the sides of the ladder. So if I find that, we're going to get that x is going to be 15. Okay, so this 15, I'll just maybe write a little note over here that if we say x squared plus 8 squared is equal to 17 squared, x ends up being 15. Okay, that's how I got that. All right, now, if we press on, I'm going to introduce a time derivative to both sides in step 5. Okay, so if I differentiate both sides implicitly with respect to time, and again, you could think of this as x of t squared plus y of t squared is equal to z of t all squared. Okay, you could think of it like that. Nevertheless, when we implicitly differentiate, we get 2x dx dt plus 2y dy dt is equal to 2z dz dt, dz dt. Okay, 2's can all cancel, and then we can begin the process of substitution. Okay, so I'm going to just eliminate the 2's. X we said was 15. dx dt is what I'm hoping to find. And then plus y is 8. dy dt is minus 2. And then z is 17. dz dt is 0. Okay, and with this, I can say that dx dt is 16 over 15. Now, the only thing we have to think about is this positive or negative? According to my diagram, right, it is sliding to the left, which in a standard Cartesian coordinate system would be negative. But if you happen to draw your diagram differently, it could be sliding to the right. So is this positive or negative is really what I need to know. And the way we get around that is just by acknowledging that we define x in this to be in the positive direction, or in our language, we would say the ladder is sliding away from the wall. The wall at a rate of 16 over 15 feet per second. Okay, and that sort of clears up whether it should be positive or negative. It would just be up to the person who is interpreting this. Is a way positive or negative? But this is a nice catch-all. Okay, so again, that 1, 2, 3, 4, 5, 6 problem-solving process is really useful. Okay, a lot of the times when you get your diagram set up, that actually tells you a lot about the equation that you're going to use. Here I saw I had a right triangle, so I knew one of the equations that corresponds to a right triangle is the Pythagorean theorem, which is how I ended up solving this exercise.